And as usual in complexity theory, what we want to do in life is to prove lower bounds on the size of the formula. So here, usually when talking about circuits, we measure the size by the number of wires, but since formulas are trees, it's much more convenient to measure it by the number of leaves, because anyway the number of leaves is about 2 times the number of wires or something like that. And we define, naturally, the formula complexity, denoted L of f, as the size of the smallest formula for f. Okay, so the nice challenge about, okay, maybe one say something that in a slide that I dropped. What's the motivation for that? Well, in general, in complexity theory, we want to prove that functions are hard to compute. So ideally, we would prove that some functions do not have polynomial-sized circuits, but unfortunately, this is too hard. We have no idea how to do it or even how to approach it. So what we do instead is to take restricted forms of circuits and try to analyze them. And hopefully, once we can prove decent lower bounds against restricted forms of circuits, it might give us a handle on how to prove lower bounds on general circuits. So formulas are one sort of restricted model that is very natural and interesting to analyze. Okay, so as usual, we hope to prove super-polynomial lower bounds on formula complexity, ideally even exponential lower bounds. But unfortunately, the best we can do is only n cubed for an explicit function. As usual, in complexity theory, this is ridiculous. I mean, we know that by a simple counting argument, that most functions have exponential formula complexity. But the best thing we can do is show one function that has cubic lower bounds. And this is called the Andreev function, and the result is due to Hastad. And the function is due to Andreev, the lower bound is due to Hastad. And the proof of this lower bound is based on a shrinkage argument. So let me just say, it's not necessary for this talk, but I will mention it briefly. So the basic observation is that if you take a formula and you apply random restriction to the variables, this means that you take input variables, a random set of input variables, and you fix them to random values, then it makes the formula shrink much more than you would expect by a naive argument. And it turns out that we can turn this observation into circuit lower bounds. This observation is originally due to Sobotokaya, and then there was a sequence of works trying to figure out what is the right bound, what is the right amount of shrinkage that's going on. And Hastad proved this lower bound by giving an optimal lower bound on the shrinkage. Yes, yeah. So recently, Avishai here gave an alternative proof. You know, you also did it in my previous slide. You said things just before I put them on the slide.
A few more I can do it with, but
Okay. So recently, Avishai gave an alternative proof of Hastad results that even improved on some lower order terms, and it's also very simple and nice, regardless of the exact parameters. Okay, so what we have now is an optimal analysis of shrinkage, which means that at least unless we get some different ideas on how to utilize shrinkage, we can't get any more mileage from shrinkage. I mean, n cubed is the best thing we can expect for the Andreev function, and in general, the best thing we can, more generally, unless we come up with a different function, a different sophisticated function, this is probably the best we can get from shrinkage alone. So this means we have to come up with different techniques if we want to tackle the open question. One such alternative approach was suggested by Karchmer-Wigderson, Ran here and Avi here. And they said that we could try to prove super-polynomial formula lower bounds by understanding better composition. So what do I mean by composition? So I'm now defining the central notion in this talk, so pay attention. We have two functions, f and g, and f takes m bits and maps them to 1 bit. G maps n bits and maps them to 1 bit. And since they both output 1 bit, the standard notion of composition doesn't apply, but we can define composition in a very natural, different way. So we define the composition as follows. The input is an m by n Boolean matrix. Now, every row is clearly an input of G, so we apply G to every row. We now get a string that we will denote A, which is of length M. And now we apply F to M, and we get the result of the composition. By the way, is it just, I mean, from here it seems like the slides are very shaking a lot. Do you also see it?
Can you make it, the focus seems to be off. I was just going to say I need my glasses from the back.
Oh, okay.
Maybe it's about that, but I'll get it.
Yeah. The slide seems to shake. You see it?
Never really had that issue.
Okay. So,
This would be easier to see. I don't know. Yeah, it's okay.
okay, so let's continue like that.
Easier to see. I don't know.
Okay, so great. So this is the definition of composition. Any questions about it? Okay, great. So now there is given this composition, there is a trivial way to compute it, which is just to compute it the way I defined it. And if you look at it, you'll see that the formula complexity, if we compute the composition in this way, the resulting formula is the size. Its size is the formula complexity of f times the formula complexity of g. Why is that? Because we take every leaf in the formula for f and we replace it with a formula for g. So in general, we get the number of leaves of g times the number of leaves of f. Now, and what KRW asked is whether this is optimal. And what I refer to as the KRW conjecture is the conjecture that this is indeed roughly optimal. Now, there is a star here because the original conjecture actually was not about formulas but about circuit depth, but it's not going to matter for this talk. Okay, so this is a very natural and interesting conjecture on its own right, but another interesting thing is that it actually implies a super-polynomial formula lower bounds. Basically, the idea is to take a very small random function, a random function with very few bits, and then compose it with itself for many times, and you get something nice. Okay, so now that we have this conjecture, we could try to prove super-polynomial formula lower bounds by proving this conjecture. So what do we already know about it? Yeah?
Maybe it's worth, I don't think it's worth
Okay.
That this sort of program works in the monotone setting. So
Oh,
KRW conjecture is true if one looks at monotone formula complexity. Because it's true, it implies, and it's very easy to prove, and because it's true, it implies that gives a different proof that monotone NC1 is different than monotone NC2, different from the proof I had with Karchmer that monotone connectivity requires.
yeah, so actually I looked at it, at the original paper, and it's not completely accurate. I mean, what the paper shows is that they don't show it's true for any function. It's true for every function for which you have a direct sum theorem.
Yeah, but you have direct sum for anything.
You have for specific functions, not for any function.
In monotone, the monotone setting.
Okay, let's take it offline.
We can take it.
Okay. Right. So yeah. So what do we know about this conjecture in the non-monotone setting? It's a good point that in the monotone setting we know a lot. So for the non-monotone setting, in the original paper suggested this a certain approach to get a handle on the conjecture. They defined something called the universal relation, which is something that's like a function but simpler. And they suggested that we could try to prove the conjecture first for the composition of two universal relations. This was actually done by Edmonds, Impaliazzo, Rudich, and Sgal, and later Hastad and Avi gave a different proof, which is simpler. And so, okay, this change was done. And more recently, in a joint work with Avi, Dima Gavinsky, and Omri Weinstein, we proved the conjecture also for composition of the form F composed with a universal relation. I'm not going to define what a universal relation is because it's not important for this talk, but really the basic idea is that it's simpler than functions, and so we already have it for the composition of two universal relations. We already have it for the composition of a function and the universal relation. So all that's left is to replace the universal relation over there in the last line with a function g. What we do in this work is to prove the conjecture for the composition of f and g when g is the parity function. So in this specific special case, we prove we prove some sort of a KRW conjecture. We prove that the complexity of the composition is at least the product of the complexities over a factor of 2 to the square root m, which is a very large factor, but it's not too bad for our context.
M is the G
M is the input length of f.
F.
Yeah, if this was true in general, not just for G, but for
Yeah, so
then it would be sufficient.
yeah, this would be sufficient to prove super-polynomial formal Lorentz. Okay, now I should mention this is actually not a new theorem. Actually, this already follows from the previous work of Hastad, but and actually they get better parameters. So why should we try to prove it again? Why should we care? Well, first, we give a completely different proof, which is always nice, and our feeling is that it seems more that this proof has a better chance of being generalizable for other G's. The shrinkage-based proof seems very tailored to parity. This approach seems to have, at least to us, seems to have more chance. But this is objective. Something objective that I can say is that we also give a new structural result. And what the structural result says is, well, okay, so one way to look at the KRW conjecture is that it says that the naive formula for computing composition is roughly optimal. And what we show is that the naive formula is essentially the only optimal formula. You can't any formula that that is roughly optimal will look in some sense like the naive formula. I'll explain exactly what we prove later in this talk. along the way, we also get a new an alternative proof of the cubic formula lower bound of Hastad. Actually, what's really going on in Hastad's work and also in the previous works is that they actually prove this theorem and then they derive relatively simply, in a relatively simple way from the composition theorem, a cubic formula lower bound. So now we also get it in our case. And the nice thing about our proof is, again, it doesn't use shrinkage, it uses a completely different technique from communication complexity. So it's always good to have alternative proofs of lower bounds that use different techniques, because then maybe some of them will be successful, will be more successful.
You can refer to Gauss, who gave 6 different proofs of the reciprocity theorem.
Oh, actually, that's a good, yeah, or to the Yao's XOR lemma, which has 5, or yeah, whatever. So anyway, so the communication complexity technique that we use is saying the follows. It's a technique of Karchmer-Wigderson, which I'll explain more in a second, but the basic idea is that it shows that every function f has some corresponding communication problem, KW of f, such that there is a tight connection between the formula complexity of f and the deterministic communication complexity of f. And the deterministic here is important. We only consider deterministic protocols. And an interesting point about it is that our proof is the first super quadratic lower bound that uses this technique. So why is this important? The thing is that, every corresponding problem, KW sub f, has a randomized protocol of quadratic complexity. So therefore, we cannot use those communication problems using techniques that work against randomized protocols, and this rules out more or less all the communication almost all the communication complexity techniques that we have. For example, by the Yao min-max principle, the fact that that we have an efficient randomized protocol means that also every distribution has an efficient deterministic protocol. So this means that we can choose a hard distribution over the inputs. And this means in particular that it's hard to use information theoretic techniques, and it's not exactly the same, but it's very related. That rectangle bounds don't seem to work. Since if you can choose a distribution, also all kinds of measures are not very useful, and so we don't. So it doesn't really seem. We don't seem to be able to use rectangle bounds, which is the bread and butter of communication complexity. So, so our work is the first work to bypass this barrier for Karchmer-Wigderson relations, which is nice. Okay, so that's it for the introduction. The rest of this talk will look as follows. We'll start with a background on the problem. Then I'll give a very high-level description of the proof strategy, and then I'll give a bit more detail about the proof. So, and let's start with the background. So, what what these Karchmer-Wigderson relations do is that they relate the formula complexity of a function f to the communication complexity of a communication problem. And basically this means that we can study questions about formula complexity by studying questions about communication complexity. And this is nice in general, because personally I feel that I understand communication better than I understand the formulas. So this gives us a grip on formulas. Now, how this problem KWF sub f looks like? Well, the communication problem is the follows. We have this function f, and Alice gets an input of f on which f outputs 0. And similarly, Bob gets a string y on which f outputs 1. Now, obviously, those strings are two different strings, so Alice and Bob want to find the coordinate I on which x and y differ. And now, again, we also need to consider deterministic protocols. Now, what is the connection between the formula complexity of f and the communication complexity of C of f? Well, the connection is somewhat cumbersome to state, so I won't state it in this talk. But for our purposes, in this talk, we could pretend that the communication complexity of KWF is exactly the logarithm of the formula complexity of f. This is not exactly accurate, but it's quite close to the correct thing, and it's sufficient for this talk. So if we assume that, what we get is that the KRW conjecture can be stated as saying that the complexity of the composition game is the KW relation of the composition is about the sum of the communication complexities of the KW relation of f and the KW relation of g. And actually this is the original KRW conjecture. Okay, so this is nice. This is just a different way to talk about the conjecture, but is it useful? So first of all, let's see how do we view this conjecture in terms of communication complexity. So, and in particular, how does the KW relation of f composed with g looks like? So as you recall, in the composition, they get m by n matrices, x and y. The inputs to the functions are m by n matrices. And what are we guaranteed on those matrices? Well, we are guaranteed that they are a 0 and a 1 of the composed function. What does this mean? It means that if we take the matrices and apply G to every row of those matrices, then we get new strings A and B, such that if we apply F to A and B, we get a 0 and a 1 respectively. Now, so this is just the definition. This is the definition of composition, so this is the definition of the KRW relation of the composition. But given this way to look at it, there is an obvious protocol for how Alice and Bob can solve the communication game. So recall, what Alice and Bob want to do is to find a coordinate and entry on which those two matrices differ. So what they can do is just to apply the optimal strategy for f on A and B, and this will give them a coordinate on which A and B differ. And then they will apply, and now, what does it mean that A and B differ on this coordinate? It means that if we look at the corresponding rows of x and y, one of them is a 0 of g, and the other is a 1 of g. So this means that the corresponding rows are actually an instance of the KW relation of g. So now Alice and Bob can find the coordinate on which those two rows differ, and this gives them an entry on which the matrices differ. So now, what is the complexity of this protocol? Well, the complexity of this protocol is the sum of the complexity of f, the communication complexity of KW sub f plus the communication complexity of KW sub g. So the KRW conjecture essentially says that this obvious protocol is essentially optimal. Questions on this protocol, on why is it true? By the way, this obvious protocol is if you look in the connection between KW relations and formulas, you get that this obvious protocol is just the analog of this obvious formula for computing compositions. So there is nothing new here. Okay, so this was the background. Now let's talk about how do we prove that the obvious protocol is essentially optimal. So why should we believe that it's optimal? So in order to gain some intuition for why this protocol is optimal, let's pretend that in each message, Alice and Bob either either send a bit about the Karchmer-Wigderson relation of f, that is, they send a bit about A and B, or they send a message about the Karchmer-Wigderson relation of G. That is, they send a bit about some individual rows of some of the matrices. In general, in communication complexity, this is not true. They are allowed to send bits that depends on all the inputs, but pretending this is correct will help us get some intuition for what we are going to do. So if we are willing to pretend that, then the point is that talking about particular rows xi and yi is only makes sense if the players already know that the output of G on xi and the output of G on yi is different. Why is that? Because if the players don't know it, they might spend a lot of effort, they might waste a lot of effort on the xi and yi, talk a lot about xi and yi, and then eventually they'll find out that xi is equal to yi. And if xi is equal to yi, then they can find a coordinate on which those rows differ, and all their effort goes to waste. Talking about those rows was completely useless. So, however, the players can only tell when a coordinate where or a row in xi, yi in which the output of G is different after they solve the Karchmer-Wigderson relation f on A and B. This is just because A and B, the strings A and B are the outputs of G on every row.
But
Yeah.
they can send G of xi and G of yi.
Yeah, they can send it, but in order to find the coordinate such a row, they will have to. I mean, they could send all of the xi's and yi's, all of the outputs gxi and g of yi, but in order to do that, they will have to send m bits or 2 m bits, and this is much larger than the complexity of f, say.
To know where, not whether.
Yeah, they have to know where the output of where gxi is different than gyi, on which row. So to summarize, it doesn't pay off to talk about individual rows xi and yi before they solved the Karchmer-Wigderson relation of f, or otherwise they might waste bits and messages on rows on which gxi is equal to gyi. Questions?
So this is only supposed to be intuition.
Right, it's only intuition. But we will turn this intuition into a proof. So what would be our proof strategy? Well, first, we wish to prove that the naive protocol is optimal. Then, okay, let's fix any protocol that solves the Karchmer-Wigderson relation of decomposition, call it capital pi. And now we are going to look at the transcripts of the protocol, of this fixed protocol, and we are going to partition them into 2 parts, which we'll call pi 1 and pi 2. And pi 1 is going to be a prefix, pi 2 is going to be a suffix, and intuitively they correspond to the 2 stages of the protocol. The pi 1 corresponds to the stage in which a player solves the KW relation of f, and pi 2 corresponds to the part in which they solve the KW relation of G. Yeah, we'll see in a second what we can actually say. So we are going now to prove 2 things. So we can make some choice of pi 1 that is of length almost the communication complexity of KWF. And it's important that it's almost. It's not fully the communication complexity of KWF, but it's close to that. And this particular choice of pi 1 has, in this particular choice of pi 1, they have not solved KWF yet. Now, okay, the second item we are going to show is that for any partial transcript pi 1 in which they haven't solved KW sub f, there is some choice of a suffix of length the communication complexity of G. That is, if they haven't solved the KWF yet, they have to spend a number of bits, they have to communicate a number of bits, which is the number of bits they need to solve G. So to get there, clearly those two items imply the lower bound that we want, because because the length of pi1 and of the pi1 from the first item plus the suffix we get from the second item will be this lower bound. Okay, so now what I called earlier the structural result, saying that every formula is about the naive formula, is actually the second item that says that in any transcript, if they haven't solved the KW sub f yet, then they haven't solved then they must communicate a number of bits which is about the complexity of G. Why is this? Why does this mean that? Okay, I want to claim that this means that the optimal protocol is every optimal protocol behaves more or less like the naive protocol. Because what it means that it really doesn't make any sense to say anything in pi1 that does not solve KWF. Before you solve KWF, you still no matter what you said, you will have to talk the complexity of G. So really, the only reasonable thing to do in pi1 is just to solve KWF. Yeah.
But again, so you claim that this shows that you have the Kiefer optimal. You basically have to solve KWF and then KWG.
So what it would show that give me an optimal protocol. And I will tell, well, look, in every transcript of, in every partial transcript of the protocol in which the optimal protocol has not solved f yet, for some definition of having not solving f, it must still communicate CKWF bits. So I can't really point out that in the second stage it does solve G, but I can at least say that in the second stage it must pay as if it was solving G, as long as it didn't solve f in the first stage.
Okay, so in what sense does this say that you are really imitating the naive protocol? It just seems to say that you are spending communication, which is the sum of the two. Right?
Okay, what it says is the following. Okay, the way I look at it is, suppose that we had a protocol that did not imitate the obvious protocol. So what does it mean that it does not imitate the obvious protocol? Well, one thing that it means is that in the first, in the first m bits that it sends, it does not solve f. And say it doesn't do so also for some more bits. What I'm saying is that as long as it didn't solve f, it will still have to solve G basically from scratch in the end. Or maybe another way to look at it is that let's look at any protocol, and now instead of defining pi1 and pi2, let's say I run the protocol just for any number of bits, just until the point in which it solved KWF. So from this point, I can tell you it will have to solve KWG. So in this sense, it's like the obvious protocol that it first solves f and then at least pays as much as it needs to solve G.
So maybe it does not solve G later, but it pays the same number.
Yeah, and actually, maybe we can also say that it solves G in a certain sense, but I'm not sure how to formalize it. We will see in the proof what do I mean by that. Okay, so we are going to prove those two items, and actually the first item is easy. I mean, if we are talking about communication complexities, and it's almost immediate that there must always, that given some communication problem, there must always be some partial transcript that is of length almost the communication complexity of the problem and has not solved the problem yet. In the actual proof of our result, we actually have to work a bit harder because we don't want we don't want really a communication complexity lower bound. We want a formula lower bound, and this roughly corresponds to proving that there are many partial transcripts like that and not just one. This requires a bit of work, but it's still really not the hard part of the proof. It's still relatively easy. Yeah, of course. We have to define, and this is also a tricky part. The second item is really the difficult part, and this is the part I will talk about in this talk. So for the rest of this talk, I will only talk about the second part. Given a transcript pi1 that is not solved KWF, find a suffix that pays, show that it has to pay at least the complexity of G. So what does proving the second item entail? So intuitively, in the second stage, they have to solve the Karchmer-Wigderson relation of G on some xi and yi. And what I'm saying here is, okay, when I say this, I mean this in the trivial manner. That is, in the second stage, eventually they find some coordinate on which those matrices differ. So in particular, they found two rows in which they differ on some particular coordinate, which in some sense means that they solved the KW relation of G. So in principle, solving the KW relation of G requires the complexity of G, but this is true only if we solve G from scratch. What really happens is that they already communicated almost the complexity of F bits in the beginning, in the first stage, and we need to show that this is not
many potential rows, so maybe
sorry?
pick the best. I mean, you have many rows to pick from, so you don't.
Oh, yeah, that's another point. But yeah, even if they didn't talk at all at the first stage, then they wouldn't know what is the best row to pick. They would all be symmetric. But the point is that solving that they've already talked a lot in the first stage, and we have to show that it doesn't make it easier to solve G on one row of their choice, which, as Avishai pointed out, maybe choosing one of the rows is easier. Okay, so our goal would be to show that really the fact that they talked in the first stage does not make it easier to solve G in the second stage. So the basic idea is the following. We know that the players communicated at most the complexity of F, which is at most M in the first stage. And actually, if we this is at most M bits in the first stage. And this means that on average, they communicated at most 1 bit per row. So I would like to argue that on a typical row, they didn't make much progress because they only communicated 1 bit on the typical row. Or I don't know, 1 bit, O of 1. On the typical row, by Markov, they spent O of 1 bits. So they didn't make much progress. However, okay, and therefore, on a typical row, they have to talk the communication complexity of G. So the question is, what happens with the non-typical rows? I mean, Markov tells you that on almost all rows, they talked O of 1 bits, but still, there might be some rows on which Alice and Bob communicated a lot. And who knows, maybe on these particular rows in which they communicated a lot, it's easier to solve G. So what we want to ensure in our proof is that they can't do it, that they cannot solve the KW sub G on the non-typical rows. And the way we will do it is to force the non-typical rows to be equal. We'll force xi to be equal to yi on the non-typical rows. So this corresponds to the intuition I discussed before. If they talk about rows before knowing that they differ on the value of G, they might end up realizing that those rows were equal and all their effort went to waste. And we actually do it exactly as is here. If we say, if they talked a lot about the row, it's going to be equal. Okay, of course, this is not that easy. Forcing equality on the non-typical rows is the hardest part of this proof. And one reason it's difficult is that if we want to force equality, in particular, we have to force equality on G, and this is a problem. What if they already found that gxi is not equal to yi in the first stage? So the point is that this is impossible. They couldn't have found out that those values are different in the first stage, because otherwise they would have solved f on the first stage. This is just by definition of what it means to solve the Karchmer-Wigderson game of f. Any questions so far? Okay. So now giving some credit, so this whole proof strategy is not ours. It was developed more or less by Edmonds, Impaliazzo, Rudich, and Sgal. The strategy I described is a bit different, but it's quite close to what they did. And they used this strategy to prove the KRW conjecture for the composition of universal relations. So our contribution in this work is to show how to extend this strategy to the composition of functions where G is the parity function. And however, it turns out to be much more challenging, or I don't know if much more, but it's challenging, even given their work. Why is that? Well, here is some vague intuition for why it's really different. So universal relations, which I didn't define, but so you'll have to trust me on this, are information theoretic objects. Somehow, if you look at the communication game, okay, I'll tell you that universal relations are communication problems that are very similar to the problem of checking equality of two strings. Okay, and this is a problem that's really about information theory. You can show that Alice and Bob must send this much of bits of information about their input in order to verify that the two inputs are equal. And in particular, it's relatively easy to show that there is a direct correspondence in this problem between information and complexity. If Alice sends t bits of information about her input, then the complexity of the problem decreases by exactly t bits. For equality, it's relatively easy to see, and it's also true for universal relations. And on the other hand, if we talk about general Karchmer-Wigderson relations, then they are computational objects. They have to do more with computing on information than on transmitting information. This is a very vague intuition, but it has very actual manifestations. For example, we can construct examples for KW relations in which Alice sends very little information, but the complexity of the relation decreases by a lot, or vice versa. It could be that she decreased the complexity by a little, but the information was decreased, but she gave a lot of information. So now, why is this discussion important? Well, if you think about the proof strategy I described in the previous slides, it's very much a theoretical, an information theoretic argument. We said, okay, in the first stage they transmitted m bits of information, so on average they gave only 1 bit of information per row. They didn't make too much progress on the typical row, etc. And so this kind of a proof strategy, this kind of an argument, works very well with universal relations because they have this property that there is a direct correspondence between information and complexity. It doesn't work so well with Karchmer-Wigderson relations. So this is the issue we are dealing with in this work. And we deal with it differently for f and separately for f and for g. So for f, we prove something that might be called the fortification lemma, which is a lemma that creates some correspondence between information and complexity for particular KW relations, and in general for particular communication relations. So fortification is a term that was coined by Dana Moshkovitz. She proved something similar for two-prover games. In her notion, what she wants to show is that she can create a correspondence between the information that the two provers get, and how it improves their probability to win the game. And here we have a correspondence between information and the communication complexity. I should say that on the technical level, those two notions are completely different, and our lemmas are completely different. But on a spiritual level, they are similar. Okay, so this is for F. For G, we use the fact that one of the lower bounds proofs for parity is actually based on an information theoretic argument, not an information theoretic argument that is as clean in the case of universal relations, but still a very clean information theoretic argument. So this means that if we just delve into this argument and expand it in our proof, we can analyze directly how information and communication and complexity interact throughout the composition, throughout the protocol for composition. And yeah.
It means that you can prove a similar result for any G with an information theoretical lower bound.
Okay. Well, I would like to say yes, but it depends. But I'm not sure how to define an information theoretical lower bound.
Okay, can you generalize it to another G which is interesting?
It would work for when G is a random function.
I'm not sure, but I'm not sure actually.
I know, yeah.
I don't actually. It's a problem because random functions don't have hard distributions, so it's not clear how to define.
But all you want is to prove that every player has to send log n bits. That's all you need to prove.
Okay, so here.
For this,
Okay, so we are jumping ahead. So let me say this: in the theory of information complexity, in the field of information complexity, we have these notions of external information cost and internal information cost. So I believe, though I'm not sure I can actually prove it, but I believe that this proof can work for any Karchmer-Wigderson relation for which there is a lower bound on the information cost.
External? And the external information?
So here we actually use internal information, but I think it should also work with external information. But the problem is that, and this is the difficulty in general with KW relations, as I said earlier, we don't have hard distributions in general for KW relations. So it's very difficult to say something about the external information cost or the internal information cost because we can't define them with respect to any particular distribution. So the thing we are going to actually use about parity is that parity has only quadratic complexity. So for parity, we can have a hard distribution. Because for parity, the randomized protocols for KW relations don't work better than deterministic communication. But then
Our statement is that every KW relation has a protocol which is quadratic, and parity is one where it's time.
exactly. So, but indeed, since this discussion leads us here, let's talk about how the lower bound for parity looks like. So, what's the KW relation for parity? Alice and Bob gets two strings, x and y, such that x has an even Hamming weight and y has an odd Hamming weight. And they want to find some coordinate I on which x and y differ. So what we want to prove is a lower bound of 2 log n. This is the complexity of G in our discussion, 2 log n. Why is that? Because the formula complexity of computing parity is n squared. So the communication complexity here would be 2 log n. Now, how do we do that? Well, it turns out that here, again, we have a hard distribution, and the hard distribution is to choose x and y to be a uniformly distributed edge of the Boolean hypercube. or a bit more specifically, X is a uniformly distributed string with even Hamming weight. Y is a uniformly distributed string with odd Hamming weight, and they are dependent. They differ on exactly one coordinate, and this coordinate is also uniformly distributed. And in particular, I'm going to call this uniformly distributed coordinate on which they differ the axis, and I'm going to denote it by J. Now the point is that when I'm giving Alice and Bob inputs from this distribution, the goal of the KW relation becomes to figure out what J is, because this is the only possible answer to the KW relation. Now, at the beginning of the protocol, Alice and Bob don't know anything about J, because from their point of view, it's uniformly distributed, even conditioned just on X or conditioned just on Y. On the other hand, when they finish the protocol, we know that they both know J, because that's the goal of the protocol. So the point is that each of Alice and Bob had to learn log n bits of information in this protocol. Okay, running late, so I'll try to do it a little faster. Each of them had to learn log n bits of information, so each of them had to transmit log n bits of information, so the other could learn log n bits of information. So 10 more, okay. So the point is that so the total communication complexity is 2 log n, because each of them had to transmit log n bits of information. Okay, so now let's go back. Actually, any questions about this argument? Okay. Let's go back to the composition. So we are going to choose, now we are going to choose a distribution, the inputs for the players from some distribution. Since I said that there are no hard distributions, I should say that the reason we can use a distribution here is that the distribution is going to depend on the protocol itself, and this is not ruled out by the min-max principle. But okay, so now that I said it, we are going to choose the inputs X and Y to Alice and Bob from some distribution. And I'm not going to describe this distribution, but I'm going to give you some essential properties of it. So the distribution is going to have the property that whenever on each coordinate on which A is different than B, the corresponding rows of X and Y are going to be a uniformly distributed edge of the hypercube. And I'm going to denote this edge by Zi0, Zi1. We will reference this notation in the next slide. We'll refer to this notation in the next slide. Whenever A and B are equal, then the rows of X and the corresponding rows of X and Y are equal. So this is the definition of, not the definition, the essential properties of the distribution. Okay, so given this distribution, we want to prove the following. If the players have talked less than the complexity of F in the first stage, then they must talk the complexity of G in the second stage, where the complexity of G is 2 log n. And actually, it works also if the players have simply hasn't, even if they talked more than this but haven't solved F in a certain sense that I'm not going to define. So for now, let's say that we just assume that they talk less than the complexity of F. So as a warm-up, let's ask, can we prove the second item if the players have not talked at all in the in pi 1, if they haven't talked at all in the first stage? So let's see what happens in this case. Well, let's recall that we have all those edges, Z0, Z11, Zi0, Zi1, Zm0, Zm1, such that whenever AI is different than Bi, they get the corresponding edge. And that's the note. Now, they are not always going to see those edges, but whenever AI is different than Bi, they will see those edges. And the point is that, okay, now let's denote by J1 and Jm the excess of those edges. So we make a similar argument to what we had before. At the beginning, the players don't know anything about those excess. And at the end of the protocol, they must have learned at least one of these excess. So again, each of them has learned log n bits, and the total communication complexity of the protocol must be at least 2 log n bits. Questions? Okay. So, but this was in the warm-up case. In the real life, they've already talked something in the first stage, and in particular, they may have talked m bits in the first stage. So this means that the players know m bits of or at least may know m bits of information on the axis J1 to Jm. And just to make an example of this difficulty, in particular, they might know m bits of information on J1. And this means that they potentially can learn J1 in the second stage by communicating only 2 log n minus m bits of information. And this is a problem because if they learn in the second stage J1 by transmitting 2 log n minus m bits of information, I mean, they won. It means that in general, they only communicated 2 log n bits during the whole protocol. And this is not the lower bound we are trying to prove, right? We want to prove 2 log n plus the complexity of f. So the solution is to condition that if after the first stage they know that m bits on J1, we are now going to condition on A1 equals B1. And by definition, by the properties of the distribution I described, if we condition on A1 equals B1, we know that the corresponding rows diff are equal, and therefore they cannot solve the protocol by finding J1. They cannot solve the relation by. Now, why can we do this conditioning? Why can we condition on A1 equals B1? Because, well, we can do it because they didn't solve f in the first stage. So this means, in particular, for any particular index, for every particular row, the probability that AI equals BI, the probability that AI is different than BI is less than 1. Or the probability they are equal is greater than 0, so we can condition on it. Okay, so what we do? So now this is just the particular case in which they know m bits on J1. What happens in the general case? So they know m bits about the excess, and now we are using an averaging argument to argue that there are at most square root m revealed excess. There are at most square root m excess on which they know more than square root m bits. Or in other words, on all but square root m of the excess, they know at most square root m bits. And the thing is that, and now we are going to condition on AI equals BI for every revealed axis. Now this is a lot of conditioning. It's conditioning on square root m things, but the thing is that if we assume that the players are sufficiently far from solving KWF in the first stage, in the end of the first stage, that's going to be okay. We can do this conditioning. So, and now after we did this conditioning, the players must solve the second stage on one of the non-revealed axes. And in order to learn a non-revealed axis, well, using the argument we did before, they must transmit 2 log n minus O of square root m bits. Questions?
So far from solving means that probably there's a strict lower bound for the probability.
So it's not a lower bound on the probability. It's actually a lower bound on the communication complexity they still have to communicate to solve f. But basically, what we are going to do is that, well, in the previous slide, they said that in the first stage they talked at less than almost KW, see, the complexity of KWF, what's really going to happen here is that they're going to talk at most the complexity minus square root m, or minus square root m log m, or something like that. So they're going, and therefore, yeah.
And then you can say something simple that if they spend dot less than m minus k, then there are at least k options.
Yeah, exactly, exactly. And
Because otherwise they could solve the entire thing.
exactly, that's the argument. Okay. So after we did all this argument, we get eventually the lower bound that the complexity of the composition is at least the sum of the complexities minus square root m. So in the few minutes I have, I'll just say a few words on some interesting lemmas that we prove along the way. So I said that we are doing an averaging argument and say that at most square root, there are at most square root m x's on which they know more than square root m. Now, I said it as if it's easy, but actually it's not. So it requires to have some averaging argument for information, and the question is, what do we mean by information, or how do we model information? So if we were modeling information by entropy, then this averaging argument was easy. It was just subadditivity of entropy. But we are not modeling using entropy. In particular, Edmonds, Imply, so Rudich and Sgal did not use entropy. They used some other information measure that they called predictability, and it's tightly related to Renyi entropy, but it's not the same. And they proved an averaging argument for this measure, but it turns out that this measure is also not useful for us. So in our work, we actually work with mean entropy as our representation of information, and we have to prove an averaging argument for mean entropy, which turns out to be not completely trivial, and we get a nice theorem out of it. The second thing I want to say is about something about the fortification that I mentioned earlier. So what I said is that we are going to condition on AI equals BI for every revealed axis. Now, as I argued, this is an event with a non-zero probability. But a non-zero probability can still be a very small probability. And in particular, it could be that this conditioning leaks a lot of information to the players. It gives a lot of information. So actually, what we want to do is to use the assumption that the players have not solved the KW relation of f to argue that the probability of this event is not that small. And intuitively, this means that we somehow want to use our knowledge on the complexity of f to say something about the information about, to say something about the probability of this event and in general about information. So this is what this fortification lemma allows us to do. Basically, it allows us to take some KW relation and to find and to fortify it, which means to find a subrelation such that in the subrelation you can't give you can't decrease the complexity by a little while giving a lot of information. So such kind of things do not happen. And this event, and this would mean that this event has sufficiently large probability. Okay, so just to summarize, in this work we reprove the KRW conjecture on, for the case where G is parity. And as a corollary, we get an alternative proof for the state-of-the-art lower bound for formulas. And along the way, we get two new tools that are of independent interest, which is an averaging argument for mean entropy and this fortification lemma. And I want to say something about future directions. So, of course, what we really want to do is to replace G with a general function. And the bottleneck in doing, sorry, I don't know if it's the bottleneck, but the bottleneck I can see now for proving it is the following. So if you recall, we had this, just a second. Okay, we had, here we had this warm-up argument of what happens if they didn't talk at all in the first stage. And actually, for a general G, we don't have such an argument. We don't even, in a sense, we don't even know how to make the warm-up argument in which what happens if they didn't talk at all. So to formalize what I mean by that, I want to consider a problem which I call the 1 out of m problem. It's tightly related, it's a very tight or close variant of a problem that was defined by Baimel et al., which they called the choose problem. This problem goes as follows. Alice and Bob are given m distinct instances of the Karchmer-Wigderson relation of G. And they need to solve the Karchmer-Wigderson relation of G on only one of those instances. Now, can we prove that this is not easy? That this is not easier than just solving a single instance of KWG? That is, the complexity of solving one of m distinct instances of KWG is at least C of KWG. It seems like it should be trivial, but so far we haven't managed to find a proof. And also, an interesting observation due to Baimel et al. Is that this is, in a sense, easier. So proving such a conjecture would be easier than solving a direct sum conjecture. That is, proving a direct sum theorem. If we had a direct sum theorem for KW relations, then this would imply a solution to this problem. But
here, not easier. It's okay if it will be a little bit.
The usual. I mean, if we lose something, then I would expect to lose the same in the KRW conjecture. Okay, so this is it. Thank you.